welcome to class. In this video, we're going to talk about inverse Laplace transforms. So if you haven't watched the video on Laplace transforms, you might want to start there. Otherwise, let's jump in. Now, because the Laplace transform is an integral at the end of the day, it's actually a linear operator too, which means taking Laplace transforms of more complicated looking expressions isn't always as bad as it might seem. If I wanted to take the Laplace transform of 2t minus 5, for example, because it's linear, I can split it over the subtraction and just take the Laplace transform of 2t, subtract the transform of 5. I can also pull constants out of integrals, right, and out of linear operators. So this is equal to 2 Laplace transform of t minus 5 Laplace transform of 1. And we actually just saw what both of those transforms are. It's negative 1 over s squared and 1 over s, respectively. Now, as you might expect, the inverse Laplace transform is simply the operation that undoes a Laplace transform. So if I know that L of little f is capital F, I could say that little f is the inverse transform of capital F. Or in other words, I can go backwards from transform land into normal land. Right? To show a couple of quick examples, to compute the inverse Laplace transform of 1 over s, it's pretty straightforward given that we know which function gives us a transform of 1 over s. Right? We know that the transform of 1 is 1 over s. So the inverse transform of 1 over s is 1. And this process should feel familiar. It's sort of like the difference between derivatives and integrals, because, well, it kind of is. Remember, the Laplace transform is just an integral, but it's a special type of integral, right? It's the integral of e to the negative st times your function, and we're looking at how to invert that process. Let's do a less obvious one. In practice, it's usually very difficult to compute the inverse Laplace transform by hand directly from the definition. And instead, we typically turn to algebra tricks to bully functions into looking like something on a table of Laplace transforms. So, for example here, I want to compute the inverse transform of 1 over s squared plus 7. Maybe I'll go look up a Laplace transform table, and I'll see one that's pretty close. We know that the Laplace transform of sine of a t ends up being, should be a over s squared plus a squared. Now, I almost have that up here, except that if 7 is a squared, that means I'm missing a root 7 on top. So the strategy we use is multiplying by a clever choice of 1. I'm going to put that root 7 there like I want anyway, and then so that I don't change the value of the quantity inside the transform, I'm also going to divide by root 7. And now that's the same number. But my inverse Laplace transform inherits the linearity property of the regular transform. I can pull 1 over root 7 out of the Laplace transform, or inverse transform, excuse me. And I'm left over with something that I actually know the inverse transform of from looking at a table. That transform is sine of root 7t.